Swayam Prabha. Digital India. Educated India.
Let us now take the case when lambda 1 is equal to lambda 2. This is known as the case of critical damping, and what it means is, remember, lambda 1 was gamma over 2 minus square root of gamma square over 4 minus omega 0 square, and lambda 2 was gamma over 2 minus plus square root of gamma square over 4 minus omega 0 square. What it means is that gamma square is equal to 4 omega 0 square, critical damping. Why I am emphasizing critical damping separately from heavy damping is because its motion is qualitatively different from that of heavy damping, and that is useful sometimes when I want to stop something from within a minimum distance when it is given an impulse. So, we will see that. Since there is only one lambda, I find that the solution x t is of the form e raised to minus lambda 1 t. However, mathematically I know that for a second order differential equation there should be one more solution. By standard techniques, one finds this solution to be e t times e raised to minus lambda 1 t. However, I am not going to take this approach. What I am going to do is, let us take limit lambda 1 going to lambda 2 in all the three cases that we studied in the heavy damping, and then see what the solution looks like. Recall, when I had taken a mass, stretched it out and released it, solution in that case for heavy damping case was x t equal to a over lambda 2 minus lambda 1, lambda 2 e raised to minus lambda 1 t minus lambda 1 e raised to minus lambda 2 t. Now, I am going to let lambda 2 go to lambda 1 and find the limit of that solution. Notice that I cannot put lambda 2 equals lambda 1 directly because I am dividing by lambda 2 minus lambda 1, and therefore, I have to take appropriate limit. So, let us see what happens in this case. I have x t equals a divided by lambda 2 minus lambda 1, lambda 2 e raised to minus lambda 1 t minus lambda 1 e raised to minus lambda 2 t. Let me take e raised to lambda 1 out, write this as a e raised to minus lambda 1 t divided by lambda 2 minus lambda 1. Inside I have, let me write lambda 2 as lambda 1 plus lambda 2 minus lambda 1. I am writing it in this form because I am dividing by lambda 2 minus lambda 1 e raised to minus lambda 2 minus lambda 1 t. Since lambda 2 is approaching lambda 1, I am going to expand this and keep it only up to the first order. The solution comes out to be a e raised to minus lambda 1 t 1 plus lambda 1 t. You can check it for yourself, and therefore, in this case x t is equal to a e raised to minus lambda 1 t 1 plus lambda 1 t. And what is lambda 1 in this case? It is nothing but gamma. Remember, lambda 1 is equal to gamma over 2 minus square root of gamma square over 4 minus omega 0 square, and this term is 0 in this case, and therefore, the general solution in critical damping case is when I stretch the spring out, a e raised to minus gamma over 2 t 1 plus gamma t over 2. You notice one difference right away compared to heavy damping. In heavy damping, the solution decayed. It is also going to do the same thing in this case. However, is going to decay much faster. This is critical damping and this is heavy damping. Why does this happen? Recall that in heavy damping, lambda 1 is equal to gamma over 2 minus a square root of a positive number, and this is smaller than gamma over 2, and therefore, the solution decays slower. So, compared to what you would have thought intuitively that in heavy damping the motion will get damped very fast, what happens is quite the opposite. It is in the critical damping that the motion gets damped very fast. So, we have given you the solution for critical damping case when I stretch the spring out or the mass out and let it go. Let us examine the other case, case B, in which case I take this mass and give it an impulse in this direction. Recall that in heavy damping the solution was x t is equal to V over lambda 2 minus lambda 1 times e raised to minus lambda 1 t minus e raised to minus lambda 2 t. Again I am going to take the limit lambda 2 going to lambda 1. So, I will have to expand this. So, write x t as V e raised to minus lambda 1 t over lambda 2 minus lambda 1 minus e raised to minus lambda 2 minus lambda 1 t, and I find that the solution in this case is V t e raised to minus lambda 1 t. Lambda 1 in critical damping case is gamma by 2. So, this is V t e raised to minus gamma over 2 t. How does this solution look? X t equals V t e raised to minus gamma over 2 t. When plotted against t, x t is going to increase initially as V t and then decay towards the equilibrium, again with the coefficient exponentially decaying as e raised to minus gamma over 2 t. In this case again the decay is faster than the heavy damping case. The third case I will leave for you to work out. I came up to this point because now I want to show you the qualitative difference between heavy and critical damping. To look at the qualitative difference between critically damped motion and heavily damped motion, let us take the case when a block is given an impulse so that it starts with a velocity v from its equilibrium point. In fact, critical damping is used in such situations for practical purposes where I do not want a body to move very far from its equilibrium point when it is given an impulse. I have already seen that critical solution is V t e raised to minus gamma over 2 t, and heavily damped solution, let me write x heavy, is equal to V over lambda 2 minus lambda 1 e raised to minus lambda 1 t minus e raised to minus lambda 2 t. To compare, I will take the extreme case of heavy damping, where gamma square is much larger than 4 omega 0 square. So, that lambda 1 which was equal to gamma over 2 minus gamma square over 4 minus omega 0 square root becomes approximately equal to gamma over 2 minus gamma over 2 1 minus 2 omega 0 square over gamma square, where I have used the binomial theorem, and this is roughly this is equal to omega 0 square over gamma, and lambda 2 is equal to gamma over 2 plus square root of gamma square over 4 minus omega 0 square, which is approximately equal to gamma itself, much greater than omega 0 over gamma. So, in this case the heavily damped solution becomes x h becomes V over gamma e raised to minus omega 0 square over gamma t minus e raised to minus gamma t, which is approximately equal to V over gamma e raised to minus omega naught square over gamma t. This is extremely heavily damped solution. On the other hand, x critical was V t e raised to minus gamma t.